Hello, I'm Dan Mapes, the course director of Augmented Reality and Virtual Reality at Full Sail University. This is Zane Gwynn, master's student, and this is Tim Tursich.
Hi.
We have been developing a augmented reality application for teaching, which I will present to you later. Okay, guys? Tim, tell us a little bit more about the mixed reality that we're seeing right now.
The third-person camera here is designed as though you are joining us in a mixed reality or a virtual reality environment, as though you might be a student joining Dan as an instructor in this virtual classroom. And Zane will be coming over here to demonstrate that feature. Much like you might do this in VR or up-and-coming AR headsets where people could share collaborative environments.
Thank you, Tim. So, as Tim said, I will be bringing Zane back in and give you an example of how this works in my classroom. But right now, I'm going to give you first an overview of some of the features and what I've added to this, and also a little bit of the background of how this app came to be and why, what problem it solves for me. So first, I'm just going to show you a few things so you know what we're going to be talking about. Right now, we have the ability in this world. I have a calculator that has a lot of the functions of linear algebra. I can create 3D frames that act as what equivalent to transforms in Unity. And in these frames, I can generate vectors and talk about what it might be to a student who is just trying to get their head around what a 3D vector is. And I'd say, well, you know, if I had this vector and I wanted to imagine what would be the sum of these three vectors, this would be equal to this plus this plus this plus this. And you can see that visibly, so for visual learners, I've got a very visual representation of what it means to deal with vector math. In addition, I can also represent basic primitives like quaternions. So a quaternion is a rotation about a vector, and I can set them equal to the rotation of a frame, for instance. So if this frame gets rotated, I can set it again. And so now I know that this is the rotation of that frame. I can add vectors in this space, and I can ask which the, now it becomes a position vector, that it's blue, it's part of this space. And if I ask, well, what would that vector be if it was in this space? And so I can reset this quaternion, and then I multiply this vector times the quaternion, and I get an alternative vector that is, as you notice, the same vector in that space. So what I'm dealing with is ability to teach students in a 3D environment what was, for me, very frustrating. When I started teaching this course 2 years ago, I had been told that the students were taught linear algebra. They knew the basics of game math, vectors, cross product, dot product, matrices. And when they came into this room, I would test them with a very simple challenge I called the dot cross challenge. Maybe 1 in 10 students was able to complete that. That made me know as an instructor that I now have to work with them on something that didn't really fit my normal course. I needed to get them to understand where the problem was, how to internalize it better, and I only had 8 days. Now, a Full Sail course runs for a month, and it runs for 8 days, so that was precious amount of time for me to do a very basic linear algebra review. So what I started to do is I would go to a normal whiteboard, and I would turn my back on the students, and I would sketch all the vectors on the board, and I would talk about all the properties, and the students were like taking notes or they're on their cell phone, I'd send them home with the homework and they would come back, they didn't understand the lecture. The reason that I am presenting this tool in a networked environment today and the problem that it solves is that I am able to not only give the lecture directly to the student in virtual reality, but I'm actually able to challenge the student at every single step of the way on basically understanding. So I will demonstrate this. It's probably best to demonstrate this, but the process of getting constant feedback from the students has really helped their ability to complete the homework. Now Zane, let's start the lesson. I'm going to demonstrate with Zane the basic first lesson on the first day of my course. And I will point out that in this 8-day course, every morning, all the students will be networked in virtual reality with me, similar to this matter. So Zane,
Yes.
are you ready?
Yes.
Let me just clean up a bit of the world. Okay. Now, first, a quick review of the cross product. So, here's a toy, and I want to ask you a bunch of questions.
Okay.
So, if this is a first vector, A, you see that?
Yes.
And this is a second vector. I want to point out that this vector here is the result. So as I move the other vector, I'm doing the cross between A and B. And do you see the cross on your calculator here?
Yes, I do.
Okay. So I want to ask you, what do you think? What do you observe happening as I'm moving B relative to A? What is the result? Do you see a property of the result that?
As B gets lower in angle, the result
Gets
changes.
larger?
Gets larger. Chart changes.
Okay, so right, as the angle gets smaller, the result also gets reduced in size. Also, if the angle is opposite, it becomes smaller. What else do you see?
As the position of B changes, the position of that changes. The
Well,
result changes.
that's true, but don't you see that it's 90 degrees?
Yes.
Here, I'm going to give you a couple vectors. On your calculator, give me the cross product of these two vectors. Select that one, cross it with that one, give the result. So do you see that the result is 90 degrees,
Yes.
right? So that's one of the major properties of a cross product. And I'm going to move along to the dot product. So we'll put this toy aside for now, but I'll go through some of those principles here. So the dot product, the first thing I want you to know about the dot product is, what is the result? Is it a vector or a scalar?
A scalar.
Right. And as you see in this toy, the length of this shadow actually represents the dot. So as I move it parallel to that red vector, and the red vector means it's of length 1, you can see that the length gets greater, or it becomes negative if they're opposite. Do you see that?
Yes, I do.
So if I gave you, and if I asked you, what is the dot product of this vector with this vector, would it be positive, negative, or 0?
I would say positive.
Aha, that's correct. And if I added this and I said this vector dotted with this,
Will be negative.
okay, that's because they're kind of generally in the opposite. But what about this vector? Now you know that this is the cross product of this and this. So what would you think that the result would be if I took the dot product of this vector with this vector?
0.
Try it. So this was the example of the first hour of the first day of my course that I bring all of my students into an environment to review all the basic primitives of vector math. Then later on we do an applied practicum of this, and I would like to show you what that would be like. Zane, could you come back in again?
Okay.
So this is an example of the back half of that lesson. We're going to bring up the pylon race. Zane, do you see it here?
Yes, I do.
Okay. So with the pylon race, as you know, this race car has to navigate around the pylons. When it crosses the line, you as the programmer, the developer, has to determine and start a timer. And that'll be in the homework. You'll see that. And the things that the car can do is, so when the car crosses the line, you have to start a timer. You have to determine that it's still on the path to the next cone. If the car gets too far away from the cone, say 3 units, it fails. If the car passes on the wrong side of the pylon, it fails. And once it starts passing the pylon, you have to determine if it goes too far from the cone, 3 units, it fails, and then you detect when it starts on the path to the next cone until it finishes the course and ends up crossing the finish line. So that's the problem. What I want to do with you now is ask you, if the car is over here, let's create the vector from here. Could you give me the vector from between the cones here?
Okay.
So you're subtracting those 2 position vectors.
Yes.
And now give me the vector between the car to the cone. Okay, so you gave me a vector from the car to the cone, but I want the cone to the car. Can you fix that?
Yes.
How would you fix it?
I would multiply this by -1.
Okay, that works. You could also subtract in the opposite order, but
Yes.
do it your way. Okay, and please delete that. Okay, so back to the dot product lesson. Tell me, is the dot product between this and this, would you expect it to be positive, negative, or 0?
Negative.
Why is that?
Because it is facing in the opposite direction.
Could you give me that dot product and prove it?
Yes.
Okay, you're right. It is negative 0.7. So, do you think if the car comes over here, and I took the difference vector, and I'll just do that for you, that minus that equals, so positive, negative, or 0 between this and this.
Positive.
So you see that if it goes from negative to positive, that could be a good way to start the timer,
Yes.
correct? Now, the next question is the car within 3 units of this path? Which means you're going to have to do projection. Let me give you another position, and that minus, just to make it more interesting. And now, could you calculate the projection of the car onto this path and tell me, is that car out of bounds? Is it more than 3 units from that path?
So I would start with creating a unit vector.
Okay, so you've now normalized the path vector. So if I look at this and I do the, if I took the dot product of this and this, now you've already told me it's going to be positive, but can you tell me, is it going to be greater than or less than 1?
Greater than 1.
Why is that?
Because this is a unit vector and this length is longer than that unit vector, so it's
Okay.
going to be above 1.
So could you give me a vector that goes to this point, the projection vector, please?
Sure.
So for the record, you're taking the dot product, and that gives you 1.5. So you're right, it is larger than 1.
Then
And then give me the projection vector, please.
Then I would take this result of the dot product, multiply it by the unit vector, and put out the length.
Okay, so now that we've got a vector that is 90 degrees from here, which is fine, could you now give me the vector that projects down to that?
So I would
I'm just going to pull this up here so that we can see what's going on. So
I will subtract this vector with this vector,
okay.
and then we'll get that.
Right. Now, I told you that 3 units, without using the length calculation, can you tell me if this is greater than or less than 3 units away? How
Okay.
would you do that?
I will get the dot product with the dot product of this vector with itself.
Okay, so what does that give you?
That would give me the square length of that vector.
So I'm asking for 3, right? So what would you be comparing it with?
The square of 3, which is 9.
Well, now that isn't right. 3.7 is not the dot product of that and that. I think we're a little bit closer. Oh, you're right. I get the same result. So it is within proper range.
Yes.
Okay, good. So now we've verified that the car has stayed on the path, and when it gets to this point, we can easily compare the this length vector with this. So clearly it's longer. It would be easy. You take the dot product of this with itself and the dot product of this with itself, and if this is longer, he's past the cone. But how can you tell if he's on this side of the cone, excuse me, or if he passed over here? So how do you know that he passed on the correct side of the cone? And I would suggest using the cross product of this with this,
Okay.
and this with this. Could you give me those 2 cross products, please? Okay, so for the record, that's the one where he passes on the left.
Yes.
And that's when he passes on the right. So if he passes on the left, what is the y value? Y is up in this world, right?
Yes, so it's a positive, so it's 2.04.
So basically we can use the sign of the value of y on the cross product to determine if the car is passed on the right side of the road. So, Zane, now that you've done this, do you think you can do the homework?
Yes.
Okay, so I expect to have that back by Thursday.
Okay.
Thank you very much.
No.
So, this is an example of how I teach my class. Instead of just having Zane, I often will have 2, 3, 4, 5 students in here and navigate between them as they struggle with each of these things. Normally, if it's just 2 or 3 students, they can all be around the same problem. If they're not, I can give them versions of it that they can each operate on themselves, and I can walk around the room. What this has done is it has just enabled me to pull understanding from them before I send them home on the homework. I hope you've learned something from this video and takeaway. Thank you very much.